Welcome everyone. It's Temple of Pwn Part 2, The Reckoning. It's Saturday again, and so it's time to pwn. So this week we're going to talk about format specifiers. Last week we had talked about, oh gosh, I can't remember what it was, I just recorded the video like 2 days ago. Buffer overflows, that's what it was. Okay, but this time it's format specifiers. So format specifiers is kind of just what you send to printf and scanf. So how you do the %d, %s, those are possible format specifiers, but what are some more useful ones that are less known are %p and %n. %p will display the value that's in the correct position in hex, and then %n will write the amount of characters printed or read if you're using scanf to the screen. Like, so if you print 15 A's, it doesn't save to the screen, but it saves to the buffer, whatever. So if you print 15 A's, then it'll save 15 to whatever points the buffer points to. And then $ is also like a unknown or not really well-known kind of availability of format specifiers. So you could do %5 $s, and this will actually print the fifth item that's in your arguments. So with these, they're argument based. So based on if you're on 64-bit or 32-bit, it kind of differs a little bit. But what this mostly means is that it'll go through registers if you're on 64-bit and then the stack, or it'll just go straight from the stack if you're on 32-bit. And the problem really occurs when it's user-controlled data that you're allowing to print, and that's what we're going to talk about today. So before we that's kind of all I had for format specifiers, so I'll talk a little bit about some other, I'll go through a walkthrough later, or after this, but what I'm going to go into more now is kind of libc and then kind of binary protections or how binaries kind of work a little bit at a low level, and then what we can actually do to exploit those. So one of those is the GOT, and this isn't the Game of Thrones, it's actually the global offset table. So this is kind of a dynamically linked table that will keep track of where the address is for a function. So what this is used for, what this is needed for, is because ASLR is usually on for most systems, and it's not really safe to be able to know where that function is at all times. So what the binary actually does when it first runs is that it'll look up these addresses and then save them to your memory so you don't have to look them up every single time. And this allows you to easily call a function in the future compared to making it unsecure and having the address hard-coded. If you're in GDB-Jeff or Pwndebug, you can just do the got command and it'll print something like this. So here we see that printf, close, read, and open all point to these addresses, but if you kind of recognize this, these are actually just simple addresses that aren't actually in libc. As you can see, this is where the GOT's at, and the offset from that's really close, so you can just assume that this is actually in the binary. And what's happening here is that this is actually pointing to the next, or not really, yeah, the next kind of structure we'll talk about, and that's actually the PLT. It kind of points to there. Well, I'll talk about it a little bit. But the PLT is kind of what helps the GOT. It's the position lookup table. So when you call a function in a binary, this is actually what's getting called, because the binary actually knows right off the bat, hey, this address is right here. So if you see like call scanf or call puts, when you actually do it, you might, and you're in IDA, you might actually see something like this where it's jumping the CS pointer of puts. And this is actually what points to the GOT, this value right here. And then if it sees like, hey, we still have or it'll jump to this address, and since this is still a user address, it's actually going to be, hey, this function hasn't been looked up yet. We're now going to go to it's usually the next instruction after the current jump, but that doesn't really matter for us. But it's going to be able to know that, hey, I need to actually look up this function, and then it'll overwrite it in the GOT. Does that make sense? Or is it, if you guys have any questions at all, just let me know, and then I can try and answer them. So we'll talk about what does this actually do for us. So for most binaries, when they're compiled, the GOT is actually writable, and it's in a section that's usually at the same offset every time for the program. So if we're able to actually find a way to overwrite this GOT, we can control what function gets called if you are able to jump around or control, or you know what the next function is. And another useful thing is that the PLT can be jumped to directly. So if we were saying we have a ROP chain going or something, instead of jumping right here, we're actually able to jump right here, just straight into the PLT, which we'll call the GOT function for us. What this does for us is because usually at the end of a function there might be a leave or something that will fix the stack frame, usually the pro or the epilogue of the function. But this usually we will have overwritten RBP. So if, when it does the move RSP RBP, it kind of causes problems for us because we might not have a direct control of RBP that we want, and it could just mess everything up for any future chains. So as I said, the PLT will call its associated function, and it's useful for op gadgets. So I'll talk a little bit about what libc is also, and this is kind of the most important bit I think of today. We'll use the GOT in our exploit today, but if you walk away with nothing besides just understand this. So libc is kind of what contains most of the functions in Linux systems. Think of it when you do hashtag include standard io.h. This is actually where it's going to be referencing most of those functions like printf, scanf, system, and all of those. And it also contains the string just straight up bin sh, at least usually somewhere inside the binary. So what how libc works is, since it's like a open source project, there's going to be lots of changes to it, and going to be able to, and the code might change drastically between different months or between different commits, I guess. So what they do is actually they'll release a new version every 6 months. It's called glibc by that, or glibc at that point, but we only really care about the libc portion. And then the most recent newest version is 2.32. But what's important about these new versions, and different versions for probably different systems as well, because some might have certain compiled features to them, is that each function or variable that you reference might have a different offset inside it. So this is why it's kind of important to make sure you use the right version and the right add-ons to it, whatever there might be. So it's because if you're using 2.30, it probably doesn't have the same offset from the base as 2.32 does. This is kind of where ret to libc comes from, is where you have to leak a libc version and maybe the binary and an address, and then find the base so you can actually know where system is and you just jump straight to it or something. So with these different versions and different offsets, we can actually do a libc lookup. So I think this is from mine, and what I used was on the stack. You can usually find the pointer to libc start main return, and what this is where when your binary is actually run, it does a bunch of different stuff where it'll start in your binary and then probably jump to libc so it can start again, or maybe it starts in libc and then actually calls your binary, but it doesn't really matter. What does matter is that there's a return address from libc already on the stack, and all you really need is the last 3 nibbles, or byte and a half. So you can see that if we use CCA, we can see that my libc version is 2.31. And as you can see, there's 3 different versions, so I'm not actually sure which one mine is, but what's important is that our main ret is actually at the offset of 26 CCA, so we can actually find our beginning of the libc addresses. The site that I'm using right here is called libc.bluecat.me. Sounds kind of Russian, so I'm not really sure if it's actually safe or not, but I've used it for a while and it seems to be fine. And then from here you can actually download the different versions. So let's say I didn't have the 2.31, I just click this download button up here, and boom, I now have the offset, or now I have the entire libc. So if I wanted a different function, or to be able to run my binary with this libc, because that's possible, but usually it takes a little bit more work to get that working. It's actually, you can just be able to see how the binary might interact, because different libcs will do different things with the heap and future stuff as well. So if you're in GDB and you want to figure out, hey, where's my libc actually loaded, you can run the command vmmap, and this will be a Jeff or Pwn exclusive command. I think PETA also has it, but in regular GDB, I can't remember off the top of my head, but I think there's a way to do it. But as you can see, what you usually want to look for is the first readable section of the libc file, and that's usually where your first offset, or where the file is actually loaded at. So it's kind of the same way with your a.out. You can see that our first readable section's at 400,000 hex, and the first readable section for libc is loaded at that address. I'm not going to try and say. So I went through that kind of quickly, about 10 minutes, I think. So we'll go into an example, kind of walk around to see a format exploit. So we have this a.out, probably ran or compiled for this fmt or fmt.c. We can check to see what permissions it has or what kind of file it is. If we do file.a.out, we'll see that it's 64-bit. Dynamically linked, we can see it points to libc, or libc and ld will be inside the regular position, so it's not mentioning a specific version. It's not really important right now. I'll probably talk about it in the future as well. Do checksec a.out. We can see that there's no position independent execution. NX is enabled, so we can't execute stuff straight on the stack. There's no canary. And then the partial reload is what we kind of care about with the GOT. If this was full reload, that means the GOT will not be writable. But usually when it says partial, that means that's going to look up the addresses in real time and then modify it so it has to be writable. So if we look at our format, we have a main, a win, and then a bunch of includes that I just used to make sure I got rid of all the warnings. And we have a character S reads in 100 characters into here, so we don't have any buffer overflow. But then it does the printf straight on this S, and then flushes standard output. That's just to make sure it actually prints. And then exits, so we don't have any return options either. So we can for sure know there's no buffer overflows here. So we'll make an exploit file. Make the one that's already there is just in case I mess up. We'll do from pwn import everything. P is equal to process a.out. Just set up a little shell or a little skeleton, I guess. If we want a GDB attach, we can. And if we were to run it, we can just kind of see. This is just how you, if you were just to regularly run the program, this is kind of what you'd get. So if we continue, we can see that it's just asking for straight input, and we just put a bunch of ones, and it just kills itself because it doesn't do anything else. So, but what we can work with is that we can send in format specifiers. So if we send in a bunch of P's, %P's, we can actually see that we can read off the registers and then probably off the stack. And if we look closely, we can actually see this repeating pattern start to show up. This is most likely our buffer. And if we were to convert this from hex to binary or hex to ASCII, we can actually see that this is our %P space over and over again. This is important to know, and we'll have to remember it later. So if we just jot this down, do 1, 2, 3, 4, 5, 6. This is going to be 6 point on. Just make a note. 6 on is buffer. So from here, we need to kind of figure out what we want to do with this binary. So what we need to do is try and get to this win function, pretty much just based on how it looks. So what we could do is say object dump dash x, I think, of a.out. Yep, and grep for win. And we can see that win is going to be loaded at this address since pi is disabled. It's always going to be at this address. So we can set that in here. Win is equal to 0x401162. Now the other important part we want is to figure out actually how we're going to get there now. So what we could do is, since there's no really return, what we need to kind of think of is how can we get there after our printf to actually be able to execute the win function. And what we're going to do is find that, or since we know the GOT's writable, we can actually overwrite that exits GOT pointer and just jump straight to win. And this is pretty standard format string exploit. What we just need to do now is say, do a little tricky move. Oh, abort FG. We'll say our binary is equal to elf of a.out. And what this does is this is a libc, or not a libc, a pwn class to load in binaries, so you can load in libcs or the binary itself. This kind of just gives us more access to different functionality for this. So if we get rid of that, we can actually do binary.symbols at win. You're probably saying, hey, you already had that. Why'd you delete it? Oh, there's no real reason, actually. We could have just kept it there. But what we can do now is also do exit underscore got is equal to binary dot symbols at got dot, I think it's got underscore exit. I have to check that real quick. Just do the print of the hex of exit underscore got x.py. Forgot I'd actually ran that. Okay, so it's not got underscore exit. Is it got dot? Unless there's just, no, I don't think there's just a got there. There you go. Yep, it's got dot exit. And we can see that it's loaded at 404038. So now we need to find a way to actually write to that, and that's where the format string exploit comes from, or comes into play. What we're going to do is find a way to write the address that's at exit got. And since we know our buffer is already on the stack, we can easily get a pointer to overwrite, or not overwrite, but write to that buffer. So if we did something like p.sendLine of %p plus space, actually here I want to do this, our string is equal to, this will come in handy later for the next part, plus a bunch of spaces times 6, because we want to have an even kind of footing on where on the stack we are, plus p64 of exit underscore got, and we do the string, and now we're to run it. Don't care about that actually opening. We can see that we have this, oh, I messed that up, $7, or not $7, $7, change this to 4. So now we're going to access the 7th element on the stack because our buffer starts on 6, but we're already 4 characters kind of corrupted into this 6. So we're going to space this out, but with another 4, and then we'll get a full stack pointer just straight to the exit got. Let's turn GDB debugging off because that's bothering me. And we can see that on our print, we're pointing straight to that value. That's important because now we're able to take this a step further and write to that buffer. So we're going to do %. I like to do it kind of this way because you don't know when you get to a dynamic function, you don't always know how big your buffer is going to be or how many characters you need to write, because you might be leaking a memory excuse me, leaking a memory and then figuring out, hey, this is going to be more characters off than last time. Now I got to dynamically fix the string, but this way we can kind of just make it work better. Exit got. Now we don't, off the top of my head, I don't know what 0x404038 is in decimal, so we kind of have to just play it by ear and probably say it's probably safe if we go to the 10th $p and switch that to an N, and then we probably need to do, if 6 is our starting buffer, we'll need, and to get to 10, that's 4 more. 4 times 8 is 32. So we want to do length of S. Here, let's actually move this up here. %10 $N. We can do the length of our string currently, and then do 32 minus. Missed a parenthesis. So now we should be at the 10th offset on the stack for our p64 function, or for our exit got. But just to make sure, we'll do a %p here. It looks like something went wrong. Format exit got should have worked. %c. What did I do wrong? I wonder if $10 Just print out the string to see what we're working with. For some reason, there's a new line in there, it looks like. No. But R. Wait, what just happened? String. This is the beauty of live demos. Okay, so for some reason our string is here, but am I just straight up overwriting? I am. That would be a problem. Plus equals. So that's what we're sending. There we go. That's what I wanted to see. So what's happening here is that our %p points straight where we want it to, and all this space is what happens when you send a huge %c buffer, and it will kind of overflow everything. So we can fix that up by doing something like z and do a p.read until the character z. You know what, this actually doesn't work too well. We'll put the z's right there. Keep this as a space. So now what's going to happen is that it's going to do the %c's, or all the characters, then we'll actually read until the z's, and then we'll just get our %p. So we don't have to worry about the buffer too much, and there. Just get that right away. But if we were to change this to an n, now all those c's should actually write straight to the GOT, and we can see that with GDB again. Move this down here just so we know we're using it. We'll finish our current function. Oh, thank goodness that didn't go. Go over to the printf. We'll check the GOT beforehand. See that our exit points to the unlooked up value. That sounded weird, but that's what it is. We check the GOT after. We can see that's the same value, isn't it? Nope, it is changed. It changed. I should probably. You guys should tell me to zoom in next time. I don't know what I just did. That was weird. Sorry about that. I could probably zoomed in to make this easier for you guys to read. We can see that it changed from the regular lookup value to now what we hoped was the win function, which I killed the binary, so GDB is now dead. And we can fix this. For some reason it didn't work though. Maybe our win is off. Or we got something else wrong. So we'll do a hex of win also. And we'll open up GDB again one more time to make sure that the address is actually right. Finish, next instruction, we'll do the GOT, 401076, next instruction, do the GOT again, get something totally different than what's in here. So that's interesting, and I think I know why, but not sure why it's off by that much. So we can print out the address of win, and we can see that win is correctly at this address. So first problem we have is that I'm writing the size of exit GOT characters. We wanted win characters. Second problem that's occurring is that now that we added the ZZs before the $n, it's going to take that into account when we're trying to write to the value. So we actually need to do -2. Now this should come up with no one should get here, or what we had in our win function. So that's kind of a simple buff overflow, but now we'll go into a more advanced where we actually want to shell through this program. And that's what we're kind of interested in all the time with Pwn challenges anyways. So do you guys want to do this kind of like a me shoot idea, or me like ask you guys for ideas and then try and implement them, or do you just want me to walk you through it on how I would do it? It's okay.
I mean, as long as you're cool with me saying dumb stuff, because this is
no such thing as dumb stuff here.
Yeah, I'm cool with that.
All right. So we'll need the win. I guess we don't actually need. I'll let you guys decide if we need win or not. Alright, so what's your kind of thought plan on what we should do first if we're going to try and get a shell? Don't all speak up at once.
Wait, are we going for shell or specifically that wins function?
No, we already got the win function. We want the shell now.
Gotcha, yeah. Okay.
So what's the, how would you, or how do we get a shell just in general, I guess? That's right. Maybe something like system bin sh, or something that's referred to as a one gadget, a place in libc memory where if you jump to it, it instantly will call bin sh for you and you don't have to worry about it. What other methods? There could be execve, which is kind of the underlying system call behind, or a different call behind system. So what we're going to try and look for is see if we can find a way to, if we were to use system, do we have a way to actually pass in values to that system call? So like, for example, something that we could control in this function is the s right here in printf. So if we can overwrite printf's got with system, we can kind of instantly win. Does that make sense? Perfect. I don't know if that makes sense at all. Hopefully it does. Now the problem with getting this to overwrite the printf's got is we do know the location, but we don't know the location of system every time it's ran. So we'll need to figure out a way to leak libc, figure out or find the offset for system, and then from there we're able to do the same thing we kind of did here, but with printf. So usually to find a leak, you need something to print out to the screen. In this case, we have this printf, and if we do a bunch of %p's, we can actually find that main return that I had used earlier, and that's kind of what we're going to do. But the problem with that comes from this exit right here, is if we don't deal with this, the program's just going to die in the first run. So what if we actually overwrote the exit got to the pointer of main? This will allow us to, every time it hits exit, it just hits the function again, and just will keep looping, so we can send in as much as we want and print out as much as we want. So that's kind of our attack plan here. So we're going to need the main is equal to binary.symbols at main. Really hoping that works. I don't actually know if it references main as a symbol in there, but it should. We're going to take the first initial string again. Don't care about printing those two. We'll do main, and we'll just check to see from here if this is actually working. So we can actually just do a bunch of any commands now. We can see that the shell stays, or the program stays open, and it just keeps reading in our input and printing straight back to us, which is exactly what we wanted. So now if we do a p.sendLine %p space times 33, because we're reading 100 characters, and each of these are 3 characters long. What this is going to do is send in all those %p so we can actually see what's actually on the stack. And we're going to want GDB also to, I'm going to want to move this down here so we don't mess up our first print. We're also going to want to attach GDB to it just to see what those values all point to. And here we can see what we have. So we have that value kind of looks like a, so if we look at our VM map, we can see that our binary is loaded at 400 and libc is loaded at 7FAD713. So that's what we're looking for. So like this one, that's a stack, and we can see that down here, 7FFE. But I'm not seeing anything that looks like a libc. I guess this one's a libc. But that one's not kind of guaranteed as much as the one we're looking for, because this is actually a libc. It might be guaranteed. I haven't looked into it too much, but this is from the call to printf, I think. Printf is actually just initializing its own variables for use. Or I'm fairly confident that's what it's got to be from. Or it could be from gets, I guess, or fgets. But since we kind of saw nothing here, we can actually just check the stack ourselves. gx.rsp, and we'll kind of continue off. So we can do an x/16gx. This will print out 16 giant words or keywords. And from $RSP onward, so this will print out our stack for us also. We can see that this is our stack value that we have down here. So we can continue down a little bit further. There's another stack value. There's another stack value. But this one, that looks like a libc value. So if we do it just to see where we're at, we'll do 16 instructions at that location. And we can see this is the libc start main. This one's always guaranteed to be in your program because it has to be called. So now we kind of just need to figure out what the offset of this is. So if this one's 6, because that's the start of our buffer, this one's 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, 33, 35, 37. So we think that's at offset 37. We just do a quick check, get rid of that. Do percent. Oh, I guess we could have checked while we were in there last time because the program is still alive. Probably went faster. 37p, and we see that, hey, this is the don't trust me. That's actually the value we want. libc start main. And now we could also do something like print, or we'll get VM map. We'll do print this address because this is where we're returning to, or we're going to leak. Oh, missed it. And do just subtract it from the current offset. And we can see that we're 26cca hex into the function. So we'll take that value. We'll do probably something like this. Percent. Oh, need to do a p dot send line. Percent 37 $p. Might leave a note saying leak libc. We want to read that in. P.read. I think if we just did something like read on, there we go. Yeah, we can do p.read until, because there's always going to be that 0x in front of it because of the percent %p, and then we'll probably just put 2 z's after it so we can get another read after. T equals p.read until z. So now we know for sure that our buffer in here is going to be that. And so let's get rid of those 2 z's. And we could do, there's a couple different ways you could do this. But since it's already in hex form, the easiest will just to say, hey, this is an int. And it's actually base 16. So that'll easily convert it for us. Oops, don't know where that 0 came from. We can subtract that, the offset, and we can actually just call this base now. And we can print it to make sure it's right. Print the hex of it. Hex.py. Oh, missed something. Okay, so I must have missed one of the z's, which doesn't make sense because I only sent in 2. Oh, I only did 1. There we go. And we can see that the value that was printed off is going to be the exact same as what we have for our loaded value for the print, or for the libc, which is exactly what we wanted. Now, since we have libc's offset, we can find system. We can do system equals base. Probably shouldn't have closed GDB just yet. We can do VM map again. Print system. We have the system address. Do a print system address minus the current libc's loaded address. We can find the offset for system. System is equal to that plus base. Now we can kind of just do the same thing we did with our exit got for printf got. So do printf got equal to binary dot symbols got dot printf. And you know, just copy the string, print it, copy these 2 strings, print it. This one I'm not going to print, and I'll show you why. So we print off, I'll print off system again. And then we want to do the format of system -2 into the printf got. I think this should do what I think it's going to do, so I'll just count that out. It didn't. Why did it not? So if we print out, oh, I know why it didn't. Okay, print out the string. I was stuck on this for a while because I was like, why isn't this working? And it took me a little bit to realize that what we're trying to overwrite is, or what we're trying to write to the GOT is this value for printf, or not printf, but for system. But we're printing, or trying to send this huge value, and I'm fairly certain that printf does not like this at all, and it will prefer if your values right here were actually less than int max, because this is definitely more than 8 bytes. This is 9 bytes, so we're off by a little bit on allowing this to actually print. So there's a couple methods that you could go about approaching this. One, we would need to do this anyways because %n only also does 4 bytes or an int max. So I'll attach GDB, it printing, or doing that again, the string doesn't really matter, but we can check the GOT, and we can see that printf already has the majority of our system string in it, and we only really overwrite these last, let's see, that's different, that's different, that's different. So it looks like we need to overwrite 3 bytes. So the most, or the lowest, not lowest, but you can either write to a full int, which is going to be 4 bytes, 2 bytes, or 1 byte, with adding different formats to the n, which I'll show in a little bit. But what we want to do is kind of overwrite this whole final part anyways. So we'll just do that. So we can do system minus 2, add those in parentheses, and then just AND it with 0x1, 2, 3, 4. What this does is just makes it, instead of a 4-byte value, or 5-byte value, I think I said 9 earlier, it's actually just a 4-byte value now. Quit this one. Now we can see that we're stuck kind of in this infinitesimal print because printing 0x 400,000 spaces is way different compared to printing, oh gosh, I don't even know. We're at 1, 2, 3, 4. We're at 5C. So that could either A, crash the service you might be attacking, B, your connection might time out by then, and I don't even know if this will even still be alive when it does finally finish printing. And the problem with this is because our read until ZZ worked last time, but it won't work this time because it still has to send that data somewhere, and it only made it faster for us because it wasn't printing to the screen, but it still has to read in the 5C, 5A, CF, whatever characters. So we're just going to kill it and do this kind of a dynamic way. So since we know we got to write at least 3 bytes, we could do this with, I didn't even think of that last time. I think I might do that this time. We can write this with 1 byte for the top half and then 2 bytes for the bottom half. We can do this with a %HHN for 1 byte and %HN for 2 bytes. So we'll need to first get the high is equal to system, and we only care about the highest order, or the 3rd byte. Not doing that, and put parentheses. Now we want to shift this over because we only want that byte. Shift it over by 32. That's not right. 16. There we go. 2 bytes. Then we'll get the low is equal to system and with 0xFFFF. So if we were to print these out, print high, low, and then system at 0x 1, 2, 3, 4. I'll just exit. This is just a show a point. X.py Oops, gotta get rid of that H's. We can see that this time we'll only be writing 16,000 bytes versus the, 935 million characters that we would have done regularly. And that's a huge difference and can save you lots of time and actually make the program work versus it not working. So the only problem with this is now we have to make sure that we actually have the right values. So if we do, we need to do this in the right method, because if we were to print out the low characters and write it, and then do the high, it won't work because all the low characters already have printed, and %n doesn't clear the buffer. If you do %n, write some more stuff, and then do another %n, it still incorporates that first stuff that was already written. So you have to make sure your math is all correct. So we for sure have to do the high first because it's most likely going to be less than, hopefully, 2 bytes versus 1 byte. And then we'll do the second right after that. %C, we do another %C, this time 11. I'll kind of show what we're doing in a little bit. $C, I'm not sure where the N is coming from. Wait, no. There we go. Okay. Now we want to do the high order bits and then the low order bits minus the high order bits. So this should give us our correct values for low and high. We can still do ZZ just to make sure, just to get through it faster. But we should be with a good confidence, because this, what printed earlier was 3 characters plus 2, 4, 5, 8 characters in total, which is still less than the 9 characters we had here. So 10 and 11 should still work for our offsets. So we need to do P64 of printf underscore got. And what we're going to have here is instead, oh, that one will actually be got, because that one's going to be the low order. What we're going to have here is 2 plus 2, because we want to write that 1 byte just to the second offset. Or to the third byte, I guess. If that makes sense. Could print stream, but we don't really care about printing it. We'll attach GDB just to make check to see if it works. Get rid of that. Can read until Z's. I think that kind of looks right. Finish that system call. Get into printf. We'll check our got first. See that printf is equal to this value. Write that there. Next instruction. And we check our got again, and we see that it has in fact changed. Now the question is that the... Oh, no, that's print. That's just read. We can see that it has in fact changed, but not for the better. So we kind of have to now troubleshoot our way into figuring out what I did wrong. I think I might have... That seems right. So we can check our string right here. %149C, which this set system, print system. Yeah, so 95, get a calculator. 95 hex is 149, which is right. Then we have 3F20 minus our 149. Nope, not hex. Minus our 149. Get 16011. So those both look right. But the problem I just did was that I still did $$ns instead of the correct values of HNs. So it's low order, or the high order one will be HHN, and then the low order will be HN. Now, if we were to check this, do the got before, save this so we can see it. And what I'm doing here is just Control Z. This background's a process, but it's still going to run. Next instruction. It's going to be panning because to be honest, I'm not really sure why it's panning. Let's go FG again. Oh, because it was background, not actually printing. that makes sense. And darn, I lost it. Whatever. Got. See that the value is the same still. That, oh no, it's got, that is slightly different. Let's just copy this over here. And we copy this one over here. See that we have the AE, and then it changes right here. But, so we have 1 byte to work correctly, but the second, these two did not work. I wonder if I did that. Yep, okay. Kill that. I also forgot the percent right here. Run that one last time, hopefully. Can finish. I'll just print it and then scroll back up and print it again. So here we go. This looks way different this time. So we have that address compared to this address. And as we can see that we have the last 3 bytes completely different now. And if we were to check, we can say print system. And we can in fact prove or show that we have overwritten the printf got with the system got. So what to do from here? Keep that going, continue, and just do /bin/sh, and we can see now we have a shell. So that's this week's presentation showing how the GOT works, kind of what libc has, how the binaries kind of work in general. Any questions, comments, concerns?
That was amazing.
Yeah.
I have a quick question. You said you were going to query us for ideas, and then you just went and rolled the challenge yourself.
Yeah, as I found out, you guys didn't like to really talk when I asked other questions as well.
Fair enough. Fair enough.
I wasn't here for most of it, but
Poggers.
I just showed up and then saw this.
So, would you ever use this kind of talent in like a CTF to get 3rd place and win money?
This specific talent? No. I would do more of buffer overflows for that.
Oh, no. Okay.
Or,
Just wondering.
yeah. For those of you watching the video in the future, that is a reference to something that happened a couple hours ago.
Oh, that's crazy. I wonder what happened a couple hours ago.
Yeah.
Oh, if there's no useful comments, that's the end of the recording. Thanks for watching.